With each intriguing picture caught by the James Webb Space Telescope, it keeps on gathering examinations from different corners of the universe, including planets inside our own planetary system. A year earlier, we studied our most significant brief ocean pictures, showing the Kina Cloud, the Stefan Quintet, and, moreover, strikingly, the captivating deep field picture. This deep field picture clearly depicts various systems resting in the vast expanse of the universe, satisfying the questions raised. The James Webb Space Telescope hasn't stopped being a labyrinth. It has, in fact, revealed objects that challenge deeply rooted cosmological theories. These amazing discoveries are now being called universe breakers by cosmologists, baffling established experts with their ability to challenge existing theories. The reasons behind these discoveries remain shrouded in mystery, throwing our speculations and theories into confusion. So what's the most recent scoop from the James Webb Space Telescope? What astounding new revelations has it uncovered that were previously unknown to us? Join us as we delve into the discoveries of how the James Webb Telescope has introduced evidence suggesting the presence of another universe, testing the conventional understanding of the Big Bang. Our universe, as we've long known, arose from a hotter, denser state through a theory called the Hot Big Bang. This idea, a major scientific achievement over the last 100 years, gained overwhelming support during the 1960s with the pivotal discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang theory has remained the dominant explanation for the origins of our universe. However, new insights have led cosmologists and astrophysicists to reconsider both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain significant traction, with the prevailing theory of the universe's origin persisting. According to the dominant view, the universe began as a smaller, denser entity in the distant past. The presence of radiation, such as photons, indicates that the universe was hotter at its origin and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels changed, where a singularity might form, and the laws of physics would break down around 10 to the power of negative 43 seconds. In such a limited span of time, minute distances and high energy levels challenge our understanding. Rewinding the cosmic clock to this speculative zero point, if the universe began as hot and dense, it would have expanded and cooled, creating vast amounts of particles and antiparticles, with excess particles annihilating each other via radiation. As temperatures dropped, the breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles known as quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense areas underwent development due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. About 380,000 years later, the discovery of the cosmic microwave background further solidified the Big Bang theory, describing the early universe as a hot, dense soup of subatomic particles steadily cooling over time. Big Bang versus steady-state theory. While most cosmologists and astrophysicists have embraced the Big Bang theory, ardent supporters of the steady-state theory, such as Fred Hoyle, continued to advocate for increasingly controversial ideas, only to face defeat in the face of overwhelming evidence. The proof presented was undeniable. It wasn't dimming starlight or reflected heat from dust. The cosmic glow showed remarkable consistency, resembling an ideal black body but with no connection to known objects in the universe. Despite this, Hoyle and his colleagues continued to undermine scientific progress by promoting experimentally questionable ideas. Meanwhile, the fields of space science and cosmology underwent significant transformations from the 1960s to the 2000s, with cosmology making especially important strides. We mapped the universe, described its large-scale structure, and examined the development, evolution, and dynamic interactions of galaxies and their cosmic populations. However, even with these advances, we encountered inconsistencies that challenged explanations within the framework of the Big Bang theory. Most notably, the absence of expected relics, such as magnetic monopoles or particles from grand unification, led many to reconsider parts of the theory. The universe we observe today seems to require forces beyond our current understanding. Despite these challenges, the expansion model and its difficulties persist, while existing theories fail to account for observed anomalies. Two approaches have emerged: refining current theories or considering alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang perspective. Inflation suggests a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and fluctuations, supporting its validity. However, despite alternative theories, inflation's scientific strength remains unmatched. Roger Penrose's work, along with his collaboration with Stephen Hawking, failed to match the development of inflation in explaining the earliest moments of the universe. Recently, attempts have been made to undermine the credibility of inflation theory by supporting formal cyclic cosmology. However, this theory is inherently flawed from a scientific standpoint, as the key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang period. James Webb Telescope's astounding disclosures. Stargazers immediately took note of peculiarities in the pictures sent by the James Webb Space Telescope beginning in 2022. These disclosures could require a reassessment of key parts of the universe's beginnings and development. One significant disclosure made by the Webb telescope was the presence of completely created systems significantly sooner than anticipated by the standard cosmological model. This abnormality challenges the laid-out succession of events following the Big Bang, where stars and black holes form originally, followed by galaxies. Such disclosures upset our understanding, like experiencing grandparents described as children in a story. Besides, later proof has uncovered inconsistencies within significant theories of the universe. For example, the persistent mistake in deciding the Hubble constant, which goes on regardless of improvements in data accuracy and measurement techniques. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight defects within the model, raising questions among scientists and physicists. While the model has gone through changes recently to line up with emerging data, some contend that these changes have been too accommodating. Thus, there is growing acknowledgement that a change in perspective might be necessary, potentially reshaping how we might interpret the universe's crucial properties. The standard model of cosmology, hailed as a win of human knowledge, rose out of Edwin Hubble's weighty discovery of the expanding universe during the 1920s. Resulting revelations, for example, the location of the cosmic microwave background radiation in 1964, confirmed the hypothesis of the universe's origin as the most plausible explanation for the universe's beginnings, describing the early universe as a hot, dense soup of subatomic particles constantly cooling over time. Reconsidering cosmology. Accomplishing the current degree of accuracy in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of boundless development, proposed in 1981, was suggested to resolve abnormalities in prior Big Bang models, further underscoring the unique nature of cosmological theory. According to this model, the early universe went through rapid, outstanding development not long after the Big Bang. While specific issues are addressed by this hypothesis, new challenges emerge, especially given the dominant belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Some detectable anomalies, such as singularities inside black holes, find support through indirect evidence. Anyway, the dazzling revelations of the Webb Space Telescope regarding the development of galaxies and the ongoing issues with the Hubble constant raise concerns that we might be approaching a tipping point where a significant modification of our current cosmological model becomes necessary. This could require a complete reassessment of the key building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its beginnings, and our place within it. The study of consciousness and quantum physics also explores similar themes, examining the convergence of theory and reality. It is crucial to investigate these foundational assumptions, given the effect of theoretical assumptions on data collection. History has shown that changes in scientific thought, such as the shift from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to profound changes in societal perspectives. A similar shift in our understanding of the universe may be approaching, driven by an impending scientific revolution in cosmology. Researcher Robert Anton Wilson argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. Investigations into cosmology may ultimately lead to the breakdown of the current model, not due to observational errors, but because of its inability to embrace new principles that fully reflect the latest discoveries. The current story should therefore be re-evaluated in light of new evidence, as the James Webb Space Telescope continues to uncover revelations that could forever alter how we understand the universe. Neil deGrasse Tyson, a popular astrophysicist and science communicator, made headlines with his comments on the James Webb Space Telescope, JWST, in relation to the discovery of evidence suggesting the possibility of another universe. The JWST, launched in December 2021, is a powerful space telescope designed to investigate the universe in infrared frequencies, allowing scientists to peer further into the universe than ever before. Tyson's remarks stem from the phenomenal revelations the JWST is already making, especially in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson didn't directly claim that the JWST has found evidence of a parallel universe, he alluded to some of the shocking and unexplained anomalies observed by the telescope, which could point to something beyond our current understanding. One such anomaly is the presence of bizarre, unexplained patterns in the distant universe, which might suggest that the laws of physics as we know them could be different in other parts of the universe, or that the universe itself could be far more complex than we had previously imagined. This could imply the existence of multiple universes, as proposed by some theories in cosmology, such as the multiverse hypothesis. However, it is important to note that while these observations are intriguing, they do not yet provide concrete proof of another universe. Rather, they open up the possibility for new theories and ideas that could reshape how we understand space, time, and reality itself.